So welcome to my video on polar. This is an introduction to polar coordinates, and it's just kind of the building blocks for something we're going to do later in the class. So a lot of you all are familiar with rectangular coordinates. Well, polar coordinates are just another system for locating a spot on the coordinate plane. In rectangular coordinates, we use x and y coordinates, and so when and you can draw a little picture, right? If this is the point that we're talking about, well, I know that this distance right here is the x coordinate, and that distance right there is the y coordinate for the point x comma y. Well, in polar coordinates, we also use two numbers, just like we do in rectangular coordinates. But in polar coordinates, instead of using the horizontal distance and the vertical distance to the point, we use the radius, or in other words, the total distance from the origin, the direct distance from the origin, and the angle. So in this picture up here, this distance right here, this would be your r, and the theta would be that angle right there. So the theta represents an angle, the angle that you turn from the positive x-axis, and r represents the distance from the origin. So it's really kind of like if you're out in the country there's no roads or anything, when you're asking for a distance, someone might say you need to go in that direction and you need to go about 3 miles. And that would be like polar coordinates, whereas if you're in the city, they say, if you're asking directions, they might say go 3 blocks this way and 2 blocks that way. That would be more like rectangular coordinates. So both of them are just different ways to describe a location of a point. So they're completely different systems. So we have the polar coordinate system and the rectangular coordinates, rectangular coordinate system. And again, the difference is what numbers you're talking about. Now notice, if we're talking about the same exact point, then over on this drawing, that is my r, and that is my theta. Same thing over here on this drawing, that would be the x, and that would be the y. This is this is the point x comma y, and this is also the point r comma theta. So that's the basics of a coordinate system. Another great example, real-life example of the polar coordinate system is this crane here that suddenly appeared out of nowhere. So this is, I don't know if you've seen these before, and whenever they're building big buildings, they use these type of cranes, and basically this thing can swivel. So this thing can turn, it can turn around like this, and this thing that's holding up can slide in and out. And so it's just like if someone told, if this is picking up a pile of stuff and someone's telling, the foreman was telling him or when he's telling him where to put the stuff, he might say, slide it out the arm 30 feet and swing the crane arm 40 degrees and then drop it. So that would be, again, like a polar coordinate system. So you can see there's a lot of use for this type of system. So one of the things we want to be able to do is convert between one and the other. And this picture is really the key to converting. Because you know that if you got the angle like this, this is the r, this is the x, and this is the, this is the y, and that's the x. Then if you learned anything in trigonometry, you know a bunch of relationships here. You know that x squared plus y squared is equal to 20, or r squared. And you know that sine of theta is equal to opposite over hypotenuse, or cosine is equal to adjacent over hypotenuse, or tangent of theta is equal to y over x. So with this information, you can figure out, given a x, y, rectangular coordinate system, you can figure out the polar coordinate system, or I'm sorry, given a rectangular coordinate pair, you can figure out the polar coordinate pair, and vice versa. And so I'm going to do one of those for you right now. So let's say that you're given polar coordinate location of 5, comma 30 degrees. So if we wanted to picture that, you could draw a quick picture and draw your angle around 30 degrees, and you know that you're going out here 5. So then you should immediately, if I'm trying to convert this to XY coordinate system, basically I'm just trying to find out what that is and that is. So we know that sine of theta, in this case 30 degrees, is equal to y, which is the thing I'm looking for, divided by the hypotenuse, which is 5. So therefore, 5 sine 30 is equal to y. And by a similar argument, you could show that 5 cosine 30 is equal to x. And so sine of 30 degrees, of course, is 1/2. So this would be 5 over 2. And cosine of 30 degrees is rad 3 over 2. So this would be 5 rad 3 over 2. So the coordinates of this point in the rectangular coordinate system would be 5 rad 3 over 2 and 5 over 2. Okay, so let's do a couple more of those. Here's a better, we'll practice this a little bit, so sorry about that blurry, a little bit bigger. So here, in this case, we're going to try to just plot the point. Okay, so just to get a feel for what this looks like. So when I plot this point, this says, because it's a polar coordinate system, this says I'm supposed to turn pi over 6, that's how far I'm rotating, and then go out 1. So right here is my turning pi over 6. Whoops, I need to get a pen here. I'm going to turn pi over 6, right? And I'm going to go out 1. So we're talking about that point right there. So the turning pi over 6 put me on this line right here, and going out 1 tells me that I'm located right at the dot. Okay, so the same thing over here. This says 13 pi over 12. We know that since that's pi over 6, this must be pi over 12. And 13 pi over 12 would be 13 of these little sections. Well, we know there's 12 of them to here. So 13 pi over 12 would have to be on this line. Get my highlighter. It'd have to be on this line. Oops, I said highlighter. It'd have to be on this line somewhere, right? And since I'm going out 4, then I know that I just have to go out 1, 2, 3, 4, and that's where my dot is. Okay, here's an easy one, 1, comma 0. That means that I'm turning 0 degrees, or I'm 0 radians, and I'm going out 1. So that would just put me right there, because I didn't leave the positive x-axis. Okay, so there's some ideas on that. Now let's do some converting. Find 3 additional pairs of, this is making sure you understand the polar coordinates. Find 3 additional pairs of polar coordinates that describe the same point as the provided polar coordinate. So, if you think about this, remember the way polar coordinates go, or remember the way the unit circle goes, if you remember from trigonometry, is you, of course, can just keep spinning around the circle as much as you want. So, if I want to write another another coordinate pair that lands me at the same place, I could do 3, and then I could just add or subtract 2 pi from this, because if I'm, 19 pi over 12, that's like what? That's 12 pi over 12, 13, 14, 15, 16, 17. Let's see, there'd be 6 of them there. So yeah, that'd be right out here somewhere, right? So if I add 2 pi to this, it's just going to come all the way around and land me right back there. So if I take 19 pi over 12 and add 2 pi to that, well, that would be 24 pi over 12. So 19 pi over 12 plus 24 pi over 12, that'd be 43 pi over 12. So 43 pi over 12 would be in the same exact location. And of course, you could subtract 25 over 12 from it also. And that means that I could be at 3, comma, and 19 minus 24 would be what? -5. So that'd be -5 pi over 12. Again, lands me at the same place. Now, one other thing that's really important for you to understand is it's possible to have a negative radius. So let's look at that for a second. I'm going to go back up here and say, okay. So notice on this one, I went 0 degrees, I turned 0 degrees and went out 1. Well, notice here I could also turn 180 degrees. So that means that I'd be pointing out that direction, right? But instead of going in that direction, I'm going to go in the opposite direction, and that's what a negative radius does. So if I did -1, comma, pi radians, which is the same thing as 180 degrees. So if I turn pi radians, that means I was facing this direction, and now I've turned all the way around, so now I'm facing that direction. And so I'm facing this direction, but I'm going to do a negative radius, which means I go the opposite direction that I'm facing. So even though I'm facing towards the negative x-axis, I'm going to go on the positive x-axis because the negative. Notice, so these two would give me the same location. And you could do that with one of these up here also. So notice the angle in the opposite direction would just be pi over 12, wouldn't it? So I could do -4, comma, pi over 12, because that's what it would be if I went back 180 degrees. So if I'm facing in this direction and I go -4, that'll take me back out to there. Okay, so those are fun. Now here's a conversion. I'm going to do a couple of these, and then and we'll do a couple converting from rectangular and from polar. So this says convert each pair of polar coordinates to rectangular. So once again, in this case, I would either draw or at least conjure up a picture in my mind, because I know that this is 1 and this is pi over 2. Oh, so pi over 2, that means, right? That means that it's right like this, isn't it? So that's pi over 2, and we're out 1. So that I don't need a triangle for that, because I know the rectangular coordinate system for this would just be over 0 and up 1, because this just means that I'm out 1 on the positive y-axis. So let's do it, it's a little bit more interesting. So in this case, we know that 7 pi over 6 radians, that's 1 more pi over 6 than 6 pi over 6. 6 pi over 6 would be right here. So I'm going a little bit past pi. This would be 7 pi over 6 right there. And I'm going out 1. Okay? So now, this is, if you remember in the good old days of pre-cal 1, or pre-cal 2, I mean, we talk about a reference angle, right? So the triangle here is really dealing with the triangle pi over 6. And so that's why this whole relationship still works. But we established earlier that the x-coordinate is equal to r times the cosine of theta, and the y-coordinate is equal to r times the sine of theta. And even though we're not in the first quadrant, this relationship is still going to work. Now you could put the reference angle in there if you wanted to, but then you just have to know that this is negative. But if you put the actual angle in there, then it'll take care of the negatives for you. So the x-coordinate in this case would be 1 times cosine of 7 pi over 6. And of course 7 pi over 6, that would be negative rad 3 over 2. So the x-coordinate would be negative rad 3 over 2. And the y-coordinate would be 1 times sine of 7 pi over 6. And of course that would be -1/2. So it would be -1/2. So that is the rectangular coordinates of that point. Okay, we'll do a couple more examples and we'll be, I better do an equation 1 too. Okay, convert each pair of rectangular coordinates to polar coordinates. So again, you should be conjuring up a picture that when you think of this is going -1/2 this way and rad 3 over 2 up that way. So we're looking at a triangle where this is -1/2 and that's rad 3 over 2. Okay, and what we're looking for is this value right here. That's my r, and that is my theta. That's the conversion that we want to do. Okay, so the r, that's pretty easy. I can just do 1/2 squared plus rad 3 over 2 squared, and that will be equal to r squared. So that's not bad. I can do that, right? So that would be what? Come down here, 1/4 plus 3/4, which is equal to 4/4, and that's equal to r squared. So r must be 1. Okay, we got r. Now theta, we need to find out what theta is. Well, once again, we have that relationship because of the triangles here. We know that these values are going to be generated by, the values that are generated by this angle are the same as the values generated by the reference angle. So I can still use the tangent relationships, because I know that tangent of theta is equal to rad 3 over 2, comma, negative 1/2. Well, actually, no, I won't do that. In this case, it's a little bit risky, so what I would do is just do this, find out what theta is, and that would tell me, let's change this to alpha. Alpha is this angle, and then from the picture I can figure out what theta is. So in this case, tangent of theta is equal to just rad 3. And that tells me that I'm dealing with, I'd either have to know my friendly angles or throw this in the calculator. But if you know that this has got to be, because this is a standing up 30-69 triangle, this has got to be 2 pi over 3. So theta would be 2 pi over 3, because that's what gives me this position. Now, if you just blindly put it in your calculator, it's going to give you a decimal number, but it'll give you this value, not that value. So you have to be aware of that. If I'm throwing this in my calculator, it's going to give me the reference angle, and from the reference angle, I have to use that to get the actual angle that I'm interested in. Okay, but the correct answer here would be 2 pi over 3. So finally, my coordinate pair would be 1, 2 pi over 3. Okay, let's do a real easy one in theory. So this thing is, the rectangular coordinates are -3, 1, 2, 3, 0, up or down, right? So if we want to get there using rectangular coordinate or polar coordinate system, the easiest way would be to rotate pi, right? And then just go out 3. And this always gives people fits because they see that -3 and they think that's got to be negative. But if I rotate pi, then I'm facing this direction, so I'd want to go out 3. Now, of course, the other option would be to -3, 0, which would be, looks like it's the same point, but this is talking about 0 radians, which means I'm facing this way, and I'm going to go -3 the other direction. So this would also work. Okay, I'm going to do one of these just to get you an idea of how they work, and then that'll be the end of the video. Okay, so in this case, convert each equation from rectangular to polar. So this is a rectangular equation. I can write this same equation using polar coordinates. And this is really what we're going for. This is the ultimate thing we want to do, and we'll talk a lot about this the first week of class also. So basically, I know those relationships, that x is equal to r cosine theta and y is equal to r sine theta. And so that's basically what I'm going to do, is get rid of all my x's and y's and replace them with r's and thetas. That would mean it would be a equation in polar form instead of rectangular form. So if I grab this, I'm just going to go r cosine theta plus 1 squared plus r sine theta, whole thing squared, equals 1. And of course that would be r, whoops, what happened there? That would be r, stop that, I guess I'm getting too over far to the edge. That would be r squared cosine squared theta plus 2r cosine theta plus 1 plus r squared sine squared theta equals 1. So I multiplied those, I multiplied r cosine theta plus 1 times r cosine theta plus 1, and that's where I got this. Okay. So the first thing I noticed is, because of course we want to simplify this a little bit, is that we have an r squared times cosine theta squared plus sine squared theta plus 2r cosine theta plus 1 equals 1. And we know that that cosine squared plus sine squared is equal to 1. So we can simplify this into r squared plus 2r cosine theta plus 1 equals 1. And if I subtract 1 from both sides, this just becomes equal to 0. And that would be a beautiful polar coordinate equation. And if the idea is if we graph this and graph this, you should produce the same exact graph. Okay,